Good morning all. Welcome to the engineering physics classes. So today we are taking the classes of our first module, oscillation and waves. And I think you have studied about simple harmonic motion in plus 2 classes. So what is simple harmonic motion? Okay, if a body is said to be under simple harmonic motion, its acceleration is proportional to the displacement and is directed towards a fixed point. For example, if we consider a particle of mass m executing simple harmonic motion, and its xp the displacement of the particle from the equilibrium position at any instant t, then the restoring force acting on the particle can be written as F, simple harmonic motion. Simple harmonic motion. Okay. So the restoring force F directly proportional to minus x. So we can write F is equal to a constant of proportionality dx. This C is called the force constant of proportionality. Force constant of proportionality. Or spring constant, or stiffness constant, or spring constant. Okay. And the negative sign here shows that, what is negative sign indicate here? The restoring force is always opposite to the direction of increasing displacement. The restoring force always opposite to the increasing displacement. Increasing displacement. Okay, that is F is equal to minus Cx. If d square x by dt square is the acceleration of the particle, if d square x by dt square is the acceleration of the particle, in SHM, simple harmonic motion. So we can write m d square x by dt square, that is by Newton's second law, force m into acceleration, m d square x by dt square is equal to minus Cx. So rearranging this equation, we can write m d square x by dt square plus Cx is equal to 0. That is d square x by dt square plus c by m into x is equal to 0. Substitute omega 0 square is equal to c by m. So we will get d square x by dt square plus omega 0 square x is equal to 0. So this is our equation. This is the differential equation of a simple harmonic oscillation. And you have studied in plus 2 classes in detail, and also you have studied how to find the solution of this differential equation. So take it as a homework and how to find. You can refer your plus 2 textbooks and try to find how to solve the solution for this kind of differential equation, and we will discuss it in the online classes. Our main topic is damped harmonic motion. Damped harmonic motion. So what is damped harmonic motion? In simple way we can say a simple harmonic motion under the action of a damping force is called a damped harmonic motion. A simple harmonic motion under the action of a damping force. Under the action of a damping force is called damped harmonic motion. DH, damped harmonic motion. Okay. A simple harmonic motion under the action of a damping force is called a damped harmonic motion. So what are the damping force? In real-time situations, almost all kind of oscillating system are under some kind of dissipative forces like friction, viscosity, etc. So what happens is, under these dissipative forces, the amplitude of oscillations decreases gradually, and after some time it gets dies away unless we supply a sufficient amount of energy to compensate the loss in energy. Okay, here we can explain with a spring block system with damping. So here we consider a spring block system on a frictional surface. At x equal to 0 is considered as the origin, and F is the restoring force acting on this spring. And if we consider the forces acting on this oscillating spring on a frictional surface, there are two kinds of force. So in addition to the restoring force, there is a damping force. So the forces acting on this oscillator are forces acting on this oscillator. Are one, the restoring force. Restoring force F is equal to minus Cx, where C is the spring constant. And in addition to the restoring force, there is another force called the damping force. Damping force F. That is here it will be due to the frictional surface. There will be a damping force which opposes the motion of the spring. Okay, spring block system. Okay, here it is considered that, it is assumed that for small velocities of the body, the damping force is proportional to the first power of velocity. For small velocities of the body, the damping force is proportional to the first power of velocity. The damping force is proportional to to the first power of velocity. To the first power of velocity. First power of velocity. Okay, so in that case we can write it as F is equal to minus, because the damping force is also opposite to the direction of velocity, and if dx by dt is the velocity, we can write F directly proportional to minus dx by dt, and if we give an equal sign, you have to give a proportionality constant. So here b is a proportionality constant, so minus b dx by dt. So that is the damping force, minus b dx by dt. Here b is called the damping coefficient. So b is a positive constant and called damping coefficient. Hence the resultant force here is, hence the resultant force is F is equal to minus b dx by dt minus cx. So the two forces acting here, so the resultant force is minus b dx by dt minus cx. So by Newton's law, we have F is equal to md square x by dt square, right? You can substitute here md square x by dt square equal to minus b dx by dt minus cx. So d square x by dt square plus b by m dx by dt plus c by m in dx equal to 0. So substitute for b by m is equal to 2k and c by m is equal to omega 0 square. K is called the damping factor. Damping factor. Okay, and omega 0 is called the natural frequency of the oscillator. Or we can say the frequency of the oscillator without damping. Okay. So substituting this equation, we get d square x by dt square plus b by m. So b, instead of b by m, we 2k dx by dt plus omega 0 square x equal to 0. Question number 3. So this is the differential equation for a damped harmonic oscillator. D square x by dt square plus 2k dx by dt plus omega 0 square x equal to 0. So differential equation for a damped harmonic oscillator. Okay, I hope you understand this video. Please carefully watch this video from beginning to the end, and if you have any questions, we will discuss during the online classes. Okay, and the next class we will discuss how to find the solution for this differential equation. Okay, so we'll see you in the next video. Thank you for watching.